All right, hello everyone. This is the fourth lecture of complex analysis. And in the third lecture, we look at the Cauchy's estimate. And as the application, we look at the proof of the fundamental algebra and the uniform convergence of the sequence of Holomorphic functions to the limiting Holomorphic functions for each of the complex subsets, those kind of like the applications from Cauchy integral formula. So for this like the lecture, we will look at key features of holomorphic functions to look at the so-called the class of metamorphic functions eventually. So in order to build up such a like the concept, I'd like to today first talk about the identity theorem. And once we establish the identity theorem, then we are able to also talk about the so-called the argument principle. And here because this like the recorded lectures related to the graduate complex analysis I'm teaching this spring 2026 at Texas State University, and I already cover the integration of winding form. So I will assume that we have some like the experience regarding this computation. And from here, we are able to talk about the open mapping theorem. And in this procedure, we are able to motivate to look at so-called the class of the metamorphic functions. So this class is related to the type of the so-called the singularity. So this is related to the concept of the pole. And whereas there is another like the case that we can control it by so-called the Riemann removable singularity theorem. So these are the contents that this lecture I'd like to cover one by one. And this is very important, like the contents to look at the class of the memory functions. But I will get back to this once I cover the proof of the open mapping theorem. Usually, I just make the record for in just 30 minutes, but it might take longer than usual because these are, I think I cannot skip any like the pieces. So let me try to do each like the step by step slow. All right. So in order to talk about the identity theorem, so this is first like the topic. So identity theorem. So this is very like the interesting theorem. So in order to talk about it, we first need to understand holomorphic functions are related to the complex, like the analytic function, which are equivalent. So that is all about the power series. It's basically all about the power series. So that somehow forces that. So we want to look at the zeros of the power series. So I'd like to say zeros of non-zero power series. This is the information we first need to talk about. So why we want to talk about these zeros? So when you imagine the form of the power series, all we can say is the information of the center and the so-called the order in the like the series expression. So those are all we can say, and also the coefficient, center, order, coefficient are all those we can talk about. So it makes sense to relate it to zero because they should be related to the like the center and the inside of the like a small neighborhood within the radius of convergence. Zero is something very natural to talk about. So the first very important like the feature of the power series is that zeros are all isolated. So we know complex analytic function is equivalent to the holomorphic functions. So that this is a key feature of the holomorphic functions that so we can distinguish from the class of the smooth functions, for example. All right, let's try to look at this. So what we'd like to say is if we assume let me say capture F should be the power series. And let's take omega as an input. So it's the summation from 0 to infinity and a sub n. Let me simply take omega to the n. So just we may assume that the center is just the at the origin. So this is the power series with positive radius of convergence. So somehow it's either the calculus or analysis like the object. So we want to assume, suppose this power series is interesting object. So this is not identically zero, not identically zero. Then we want to look at the zero set of this power series of this power series, within the disk of the convergence, disk of radius convergence must be must be discrete. So so it uses the following. So let's look at the proof. So what we know is this is the series and this is not identically zero. So since f is not identically zero, and we know this capital F is written as a summation from n to 0 to infinity with each of the term, so that we are able to find the at least smallest index. So there exists, let me just use the quantifier. So we are able to find a smallest natural number. So say, or let me say the integer. So say, let me say m, such that at least this coefficient should not be zero. So this is definitely guaranteed. So because, and this follows from the variable principle, by the way. So as long as we know the m index here, then we can extract this like the index from the given power series. Then we are able to write the given power series. So let's just use the same input. So same power series as what? So we can just take this order because, so this is a small list. So previous like the stage or coefficient is a zero, so that it just start from the order of m. So that we can just take it as a common like the vector. So then we can extract the remaining term. Remaining term. Of course, this guy should be also written as a series, and we just shift the index of the power series so that even we write as a omega to the n for taking the summation index. So the corresponding coefficient should be a sub n plus m because we took the corresponding like the order of omega already. Then it is now clear that if we plug in, because we just assume the center is at the origin, so this does not like the cause any like the reduction of information. So we can just plug in zero. I mean the center. Then if we plug in like the zero, then we know then at least a sub n, a sub m, we know this is non-zero. So g of zero is non-zero, and we know G is holomorphic because it is written as a power series. So this implies G must be continuous. So that from the definition of the continuous function, I mean, in terms of epsilon and delta, so if the function value at the zero is non-zero, then by using the continuity, we can just extend such a like the non-zero value for the small, at least small neighborhood of the zero. So by using the continuity, by continuity of G, then we are able to find at least small neighborhood. Let us use rho. There exists rho such that so this function G is at least never zero within this like the small neighborhood for any omega strictly less than rho. This is guaranteed by, this follows from just the definition of the continuous function. So what does this tell us? This tells us that, so on this small neighborhood, let's say B sub rho at zero, so the only zero of this function. So because for the remaining like the holomorphic part of capital G, so all we can do is we should just multiply by omega to the m, and omega to the m is only zero when omega is zero. So that we can see that the only zero of f is nothing but zero. This is the only possible choice. So we can say thus zeros are isolated. So if we take another like the zero, then we can just use the same argument to find the small neighborhood. And in that small neighborhood, only the center is the only possible like the spot to make it to be zero for the target function. So this gives the proof. This gives the proof. So from here, we can say something interesting. So one corollary from here. So I'm not sure how many like the numbers I need to put. Let me just put just a lemma and corollary. So what if there is a sequence given same power series f as same, then if we are able to find the sequence, so this is a sequence of distinct zero of the given power series converging to the point interior. Let's call it by omega naught inside a ball of convergence. Then what can we tell? So because from this lemma, so we were able to establish such a like the argument to separate each of the zero because we assume f is not essentially zero. And on the other hand, this like the assumption of this corollary says if we already have the sequence of distinct zeros that converges to the point in the within the ball of convergence, this cannot be happen. So this forces this power series must be identically zero. There is no other possible choice. This is clear from this like dilemma. So now we are ready. We are now ready to establish the identity theorem. But let me just say this more precisely. So as a proposition, equivalently speaking, let me say as just a remark. And I can say this remark with the name. So the local uniqueness of accumulating zero set, let me say from. So we can now state like this. So rather than looking at the power series, we can simply just look at the holomorphic map. So let F be omega inside of C, and omega always meant domain. Domain means connected and open. That maps to C, be a holomorphic map. Let's assume this function is holomorphic, and let's just also assume we have some point in the omega, so that we can just use the corollary assumption. So if there exists a sequence G sub k in omega, such that C sub k is never same as the target limit point, and this C sub k goes to p, and each like the sequence makes the zero for each k. Let's just assume this guy. Then from the argument that we already established, because at point P, we are able to write down F as a power series, and just so we repeat the same argument, then that shows that because there should be no like the accumulating like the sequence of zero, that's not possible. So at that neighborhood, this holomorphic function must be identically zero at that like the ball of radius. This is we already guarantee. So this says then there exists some positive like the radius such that inside within this like the ball, this function must be zero for any point within this ball. So in other words, the target holomorphic function under this assumption existence such like the sequence of the zero set, then f vanishes identically in a at least small neighbor. This is guaranteed. And identity theorem, the desire is we actually want to say so the from the third like the lecture, we saw from Cauchy's estimate that holomorphic function behaves something similar as polynomial. Of course, under certain assumption, but it's related. And if you like the intuitively imagine the behavior dynamics of the polynomial, if the polynomial is like the zero, I mean identically zero in some small neighborhood, then we actually expect this such a like the polynomial is actually zero everywhere. So some similar like the phenomena might happen for the holomorphic function. This is the spirit of the identity theorem. And before I go further, the reason we call this a local uniqueness is that so rather than just applying such a like the argument to the target like the holomorphic function f, so we usually use this for the comparison two functions and take the subtraction, and this is targeting function to make it really identically zero. So two function must be equal. So this is the standard way to establish the uniqueness. So now let's talk about the identity theorem. So the argument is very beautiful. So let omega is inside of like the complex plane. And as I said, with this is domain, connected open set. And connectedness matters. So from topology, so of course this is already quite abstract to really like appreciate the meaning of the like the abstract definition of connectedness from topology, like the class, but it says the given set is disconnected if there's a proper set which is simultaneously open and closed at the same time. So the connectedness means we exclude such a like the existence of any proper subset which simultaneously becomes open and closed at the same time. That cannot be happen. That's the meaning of that's a abstract like the concept of it is like a connectedness that really matters. So we also assume there are two functions. Of course, there are several like equivalent like statements of the identity theorem, but let me just state this version. So omega to c, let's just assume they are all holomorphic. We know this, then what we want to establish is that in fact these two functions are identically equal. So in order to say that, so we will assume the following somehow strong, but something very like the weak. If you just look at these like the class of the smooth functions, this like the assumption. So except the holomorphic function is not sufficient to guarantee two functions are the same. So suppose there exists a subset in omega having an accumulation point. point P in omega such that F is same as G for any point in this like the set accumulating the point of omega so that we are able to find the sequence. So then you might guess, so we already established some like the local version of the established two functions are. So f minus g, so that we can talk about the zero, so that we already established f minus g is identically zero in some small neighborhood of the given each of the zero. So we want to claim that this phenomenon is global. So f is same as g. F is same as g. So on omega. All right. So this like the statement is interesting in a sense that so we just investigate the two holomorphic functions coincide in the level of the just a sequence. Then there's no other choice except those two functions must be identically the same. So that if two functions are distinct, different, then we are not able to find any of the like the conversion like the sequence in the given like the domain that so each stage they exactly overlap. That's not possible according to this identity theorem. So the proof is also quite like the standard. It's topology proof. So as this is important, let me also go over the proof in detail. So the idea strategy is to use the definition of negation of, let me say, the negation of disconnectedness. So according to the disconnectedness definition, it says proper closed open set subset of omega. So what we want to make is we will establish the set in omega, subset in omega, which is non-empty, closed, and open. So that we have the closed and open subset. Then according to the this like the situation, so there's no proper subset. So therefore, such a like a subset must be same as the entire like the omega. That's the idea. So in order to establish that, so let's just make construct the following set. So E, so that we collect the point from the given domain. That is, so we wanna say that I would like to look at this H. So yeah, before I talk about like the such like the concept, so let me just reduce the situation to just look at the zero. So let me just move this to the here. So let's just set new holomorphic function f as just a f minus g for convenience, so that now we already have, of course, this guy is defined on omega, so that we just reduce to just look at the zero of this h if you look at the just difference of two functions. So now we will just declare the set capital E. This is a subset inside of omega. So if the point belongs to this E, then we are able to find a small neighborhood. Neighborhood means open set containing that like the point. Small neighborhood in omega such that if we restrict this holomorphic function to H, then this is identically zero in this small neighborhood. So this is the set we like to construct. So we want to claim E is non-empty. We'd like to claim E is open. We'd like to claim E is closed. then once we establish all these claims, then from the negation of this connected like the set so that it established the proof of the identity theorem. So that's the strategy. So let's just check one by one. So why we can claim this like the E is non-empty because we already have the assumption that there is a accumulating like the set that makes H to be zero. Then from the remark, we know that we are able to find the small neighborhood that this such a like a function should be identically zero on that within that small neighborhood. So because by the hypothesis with remark, we know we know H at this like the sequence is as a zero for each k, and z sub k goes to some like the point in omega. This forces that H restrict to u sub p is zero by the remark. This forces that p must be the point of this set so that we at least use this like the assumption. Let me say rather than hypothesis, let me say assumption. By assumption, so that at least this set is now non-empty. Then why this set is open? It follows from the definition. So that the what's the definition of the open set? So it should be written as a union of a small ball. And by the it's like the definition of E. So as long as the point is the point of the set E, then we are able to find the neighborhood that makes the given like the H to be just a zero, then we are definitely find a very small neighborhood in that like the neighborhood because neighborhood already open set. So this is actually clear. This is clear, obvious by its definition of E. And lastly, we need to see why this like the E is closed set. Then we just need to see it suffices to say if C sub k, the sequence in E is convergent. Of course, in omega, say Z naught, then this Z naught must be the point of E. This is what we need to now claim. So then why this is now a guarantee? So because we assume the sequence goes to like the Z naught, so since Z sub k as k tends to infinity, this tends to Z naught. So this is what we need to show. Z naught belongs to E. Then we are able to find small neighborhood. Actually, this is true for any neighborhood. For any neighborhood of Z naught, then we have the index such that for any like the index greater or equal to capital N, so Z sub k belongs to U sub Z naught. This is guaranteed. Okay, then, but at the same time, since Z sub k is all the point of E for any k greater or equal to N, any k greater or equal to N, so so for each N, for each k, we are able to find this small neighborhood such that H restrict to this guy. This function is identically zero. This function is identically zero in that restriction within this like this small neighborhood. Then on this guy, so you can actually choose any like the small neighborhood here because this holds for any neighborhood so that we can just shrink if necessary. Then in this like a small neighborhood, this is definitely guaranteed. This is definitely guaranteed. What does that mean? Though this already full because this is also the neighborhood. Of Z not as well. This is also neighbor of Z not as well because the use of like the K use of ZK. So we are also able to make this to just contain Z not as well. If we just so this is definitely guaranteed. So so this tells us Z not is also the point of E, and this completes the proof. So you can just try to clarify this like the argument if you feel that should be helpful. So we'd like to show Z not belongs to E. Then what we need to show is we need to find a small neighborhood that makes the restriction of the function h, the function must be identically zero in that like the small neighborhood. And we know z sub k goes to like the z naught. So that so we first like to look at the some like the small neighborhood like the u of like the z naught. Then greater or equal to that like the index. We know already each of the z sub k belongs to that small neighborhood. And if we fix one neighborhood, one like the index k, then still we are able to find some small neighborhood like that is of k, that this h is identically zero in that small neighborhood. Then if we just shrink by taking the intersection, then and on the other hand, so this like the each of the like the u sub z naught and u sub z k or like they contain this like the z naught. So therefore the just follows as I already explained. So this is the so-called the identity theorem. All right. So from this like the theorem, we can now say, so this is now the very like the first part of this like the lecture. Now let me talk about the argument like the principle. So so from here, so far we look at the information of the zero. Especially if we are able to find the sequence of the zeros within the in the domain of the Holmberg function, then such a like the phenomenon cannot happen other than just a zero function. So it matters to just look at the information of like the zero. So uh, on the other hand, we can actually look at the following. So we can talk about the so-called the concept of the like the order. So we say the of the each point, let me say P is the order K, the zero of order K, the zero of order K of a holomorphic function. Of course, this omega contains the point P. So if we are able to find another holomorphic function, H from omega, such that F can be written as a z minus p to the power of like the k times h of z, such that h of p is non-zero. So if we are able to find such a like the oh, so so for a function, then yeah, we call this is the order. So now and usually, in fact, we want to exclude this point with several like reasons. So of course, this can be taken as a definition, but in order to talk about the singularity, so we usually exclude this like the point. We will look at this later on. So of course, this P was originally considered to contain this like the point. So, but let's just rewrite like this, like the form. So, of course, actually, it doesn't matter because we will prove so-called the Riemann, like the removable singularity theorem. So what I already said is actually already correct, but even so, I'd like to be consistent. So, with this like the concept, so the reason I want to show this is by looking at this like the form of the DDF. So we can take the derivative. We can take the derivative. Then the derivative gives us k times z minus k to the power of k minus 1 h of z plus z minus p to the power of k times h prime. So what if we are looking for the information of the order of the zero of the given holomorphic function? Then how can we extract the information of k? Now we have k here. Now we have a k here. So the way to somehow naturally extract is just by dividing f prime by given function. Let's consider this guy. Then we are able to rewrite this expression as we already wrote. So we know this expression is same as z minus p to the power of k times h in denominator, and numerator comes this guy. We have this guy. Then let's just try to simplify. Then from the common denominator, so we can cancel for each. Then we can see the first expression. It becomes k over z minus p. So we get some like the familiar expression related to so-called winding form. And the second expression, so this p to the power k cancel together, and this becomes h prime over h. So if H and H prime and H are all like the complex differential, which is equivalent to holomorphic map, then the ratio form is also complex differential for sure, which is also holomorphic. So once we get this expression, then it is natural to think about the winding form with the quotient integral theorem. So now let us just take the loop integral so that we will take the loop integral along the center at P, and let's just take the small neighbor. Let's call it by R, small r, of this expression, F prime over F. And for the winding form expression, so we know this is related to pi I, so let's also divide by that. So once we get this one, then the second expression, H prime over H, so the quotient integral theorem guarantees it must be vanish. And 1 over z minus p, if we just rotate exactly one cycle along the like the counterclockwise direction, then we know it becomes 1. So this must be the order of f at point P, which is K. So now we know we are able to extract the information. We are able to extract the information of the order. This is we call the argument principle. Of course, there's a rigorous like the statement in terms of the numbers of like the zeros and numbers of the so-called poles. But before I talk about the like the concept of the pole, so I'd like to say one small like the remark. So at this like the stage, so we somehow uses the like the intuition regarding the like the ball. So that there's a point like the P, there's a point P, and we just took this like a small neighborhood so that we make this guy to take the integral. So this somehow makes sense in the following sense. So if we take the holomorphic function with the quotient integral theorem, then we know the loop integral should be vanished so that And the what's the like the condition of the Cauchy-Riemann equation? This is so-called the curve-free condition. So that we actually apply Green's theorem. Green's theorem. So that Green's theorem guarantees that if we just change the loop a little bit like the shrinker than the given one, then from the like the curve-free condition, this like the Green's theorem tells us with the Cauchy integral, like the Cauchy-Riemann equation, then this part, the double integral should be just a zero because the integrand is just zero. That's the curve-free condition. Follows from the Cauchy-Riemann equation. Then we are able to shrink it to the like the point P, the center. So the integral is actually taken with just a singleton set somehow because the integral value is not changing. It follows from the Green's theorem. So that's why Cauchy's integral theorem makes sense for the holomorphic function in the like the disk whose like the boundary is the circle. However, so if we want to detect the information of this like the singular point like the z, so because this is related to the winding form, this information is the information of the winding form, meaning that we should not say the winding form, this like the corresponding vector field, this point P is naturally well defined. If this is like well defined within the disk, then the fundamental theorem of the line integral guarantees that the integration should be zero, and we know that's not the case. The index or the winding. So index is never, it's not guaranteed to make it to be zero. So that it makes sense to only talk about such a like the annulus rather than just talking about just the disk. So if I'd like to heuristically say, if we want to consider an effect of singularity at point P, so think about the winding form, then we should exclude such a like the point. So it is natural to extend the annulus domain. Let me say annulus like this, which is defined as a, if this is a point in the complex plane, this like the absolute value is strictly greater than a small r, but greater than capital R. This is something natural because even this like the target function has the singularity at some point, for example, like the center. But if we just take the annulus, then you can just shrink this like the small like the circle to the point. If there's no singular like the singularity, then eventually we can just make to just we can just fill this gap. But if that's not cannot be the case, then this is sort of our like the best to do it. So so from here, so we are able to talk about the annulus somehow very natural way, but at the same time, we need to consider the concept of the like the pole. So we will say the following. So this is the concept of the pole. And also I might talk about like the zero maybe again. So let me say types of the singularities. And it is also clear. By the way, all like the singular points are isolated. So let me that in the sense called by types of isolated singularities. That is the following. So let f be a function from omega that we exclude this like the singular candidate that maps to C. And with this exclusion, so this function is LS holomorphic. Then we will just split three possible cases. So number one, we'll say F is removable singularity. If that's the case, we can feel this like the singular like the point. So if there exists actually unique, but uniqueness just follows from this like the just the existence. So let's just say exists a holomorphic function. Let us say just a f tilde from omega to c. such that, so if we restrict this function to omega complement of this point, this is same as that. In such a case, we say this point is removable singularity. So the second concept is most important. We will say this point is pole. This point is a pole. If we are able to find the integer, if there's a integer and also a holomorphic function, let's say g from omega to c, such that, so if we have a zero, then we already extract the term like this. If we had a like a zero of the order m, or just take the opposite. Instead of just extract the term from the right hand side, we extract the term from the left hand side, so that it is natural to just take the form of like the f, and we say p is the target point, so we just take this part rather than the right hand side for the zero, so we just take the opposite. So this is same as g for any point except p. Of course, we exclude z equal p, so that definitely we are able to write f can be written as g over g z minus p to the power n. This is also valid. So, and there's also the possible case, neither of them. So we will say p is essential singularity. It is essential singularity if it is neither removable nor a pole. Right? And what we can say is that, so for each of the cases, if we just consider the analysis, it is safe. We can always just exclude the like the target point P. So, and we can still claim the holomorphicity for such a like the function on the animals. So this is one like the benefit for them. So before we talk about the concept of pole, so we first want to claim the famous theorem of Riemann, one of the famous theorem of Riemann, that we can indeed just remove the singularity for the like, very like the first case. So this is the theorem that I'd like to say Riemann removable singularity theorem. So because in the detail, we actually rely on this like the useful proposition. It says the following. So we have the omega in C, which is open. And we also have the point in omega. And we say F omega exclude this point is holomorphic. Then we will assume only one possible condition. So if you look at this like the pole condition, as z tends to p, then because the denominator tends to zero, so that the entire ratio might tends to infinity, because this g is just a reasonable like the continuous function in this like the, if this omega is such a small pole, so that it goes to infinity for the absolute value, so that we will exclude such a like the case. So we assume f is bounded. F is bounded in some punctual neighborhood of P. If this is the case, then F extends uniquely. to a holomorphic function f tilde that maps from omega to c, so that we pass through this like the singular like the point. So this is the very like a famous like a theorem, and I actually invite you to just investigate the proof by yourself. Let me just give you the like the one like the famous proof uses Cauchy estimate. So because we assume f is already bounded, so that let us just choose small ball such that this ball, including the boundary, this all belongs to omega or belongs to omega, and we from by the assumption f is bounded in this like the small ball. So say z minus p, this is less than r, but we also exclude when z equals p. Then so this is related to the annulus like the expression. And if we think about the like the using the Cauchy integral formula to recover the power series expression, so that as long as we have the annulus like the expression, then by using the like the smaller like the boundary condition, we can also expand rather than the power series, but the so-called the Lorentz series like the expression. So let's also write such like the function as a like the Lorentz series. So if you are not confident on this like the part, then just look at how we come up with the power series expression from the power like the Cauchy integral formula for the like the larger like the radius of the like the circle. And once you just apply that argument for the smaller like the circle, then you get the so-called negative like the or like the orders. That's the argument. So that we are able to so-called the Lorentz series expression. So the summation from negative infinity to infinity of a sub n c minus p to power of n for any like the z which is strictly less than r but greater than 0. So now we have this guy, and moreover, all these expressions are indeed coming from the just Cauchy integral like the theorem. So moreover, the expression of each of a sub n is indeed coming from the Cauchy integral theorem, Cauchy integral formula. So it is 1 over 2 pi I, and its integral with f of c over c minus, so now the center is p, to the power of n plus 1 dx c, and we are taking the loop integral along the circle whose center is like the p, and let's just take the small like the rho, and this like the rho is less than r. Now this is guaranteed, but here the important like the point is this is true for any n, not just the non-negative integer, but also negative integer as well. So now let's just take the benefit for just looking at this expression of the coefficient. So now if this n is negative m, let us say negative m, of course here I meant m is greater or equal to 1, natural number, then we, because assume f is bounded, so a sub negative m, so let's just also put the absolute value to control this like the upper bound. Then it is clear that we first have the 1 over 2 pi for the constant, and the from the like the integral, so that we also will get 2 pi rho. This is also guaranteed, and we also will get supremum of the absolute value of this given function, which is bounded by the assumption. And of course, this c minus p is, we are just looking at just a root of the like the radius of rho whose center is like the p. Then we know this part is finite by assumption. Then these are all gone. So as what we can see is that, so as rho tends to zero, this tends to zero. And we know a sub negative m is fixed like the complex like the value, so that this guarantees that all a sub negative m should be zero for any m greater or equal to 1. What does that mean? So for this like the so-called Lorentz series, expansion, wrong select the expansion. So all negative degree just vanish. So it is just a power series. That means F mass polymorphy and the probe is over. So what we can at least guarantee is that so if we have the singularity that for the point P, that is the given function is bounded, then we can actually remove such a like the singular like the point. All we actually need to worry is those two possible cases. And with many reasons, we will look at the case of the pole. And now let me try to explain the arg so the open mapping like the theorem. So before I talk about the open mapping theorem, so let me just wrap up the argument like the principle just a bit. So why this like the argument principle is kind of interesting. So even I just mentioned here in terms of the zero, but now we have a definition of the pole so that in the like the given like the domain of the holomorphic function that might have the zeros and the poles. And if we just argue something like this, then just by looking at just some like the note for argument principle. So we can realize the following. So if we have a point P, and we just choose the small neighborhood of like the R, the radius of the ball R, whose regular radius is just R, so that we have this guy. All right. Then we have some target function f. We have some target function f. Then we are able to parameterize this like the loop, say in terms of t, so that this can be written as a p plus r times e to the it. So if we just rotate one cycle counterclockwise direction, then so what if this like the point P is the zero of this like the holomorphic function? Then if this is like the zero, then from the like the argument here, from the argument like here, we know how to extract the order of the like the zero, order of like a zero. Then what is the like the meaning, the picture of this situation? We are actually rotating k times. So it's like rotating k times. If the p is the zero of f of order k. So indeed, this is coming from the effect of the winding form. So this is what I'd like to just mention. So indeed, this is coming from the winding, rather than winding form, let me say winding number. So this like the picture clearly makes sense. Clearly makes sense. And from here, now we are ready to state. Now we are ready to state so-called the open mapping theorem. So at least let me try to finish this like the import like the statement, open mapping theorem and the proof. So we will have the following. So let omega inside of C be a domain. Then we also will have function from omega to C, which is holomorphic, but also non-constant. Then we have the image of this guy is open. This is open mapping theorem. So one like the just a note, this theorem does not hold for in the like the smooth like the category. So for example, if you just take the function g from like the C to, for example, like the C. So for the point, if you just map this to be like the Z norm square, this function is infinitely differentiable. But you can, as you can see, the image of this guy is from 0 to strictly less than infinity. This is not open. So open mapping theorem does not hold for the smooth functions in general. So we need to require the holomorphic functions to have this like the phenomena. And why this is also interesting. So if we accept the open mapping theorem, so let sigma sub g be a compact Riemann surface. Compact Riemann surface. Then we can take any holomorphic function. Then what we know is that the image, the image, then by the way, this is compact and continuous function. F is continuous function, so this must be compact by just using the fact that the image of the continuous function under the compact, like the domain is compact, and also this is open, follows from the open mapping theorem. Then we know compactness implies closeness. So it makes closed and open at the same time. And C is already like a connected set. So this is only possible if F is constant. So any holomorphic function on a compact Riemann surface must be constant. So this is the reason that we need to make the pole so that we should look at the class of the metamorphic function. And from there, so that we can just establish the Riemann-Rolle theorem in terms of the metamorphic functions and the metamorphic form, because there is no non-constant holomorphic function. So, and this is coming from this like the important like the theorem. So the statement of the open mapping, I guess the proof of the open mapping theorem uses what we established from this note. So proof of open mapping theorem. And let me try to finish this like the lecture with this type of proof. All right. So in order to show the image of this omega is open, so let's just say use the definition of the metric topology. So let us take any point from this image. Let's take any image. Then we need to show, it suffices to show small neighborhood of this point such that so the small neighborhood belongs to this image. Then it established the proof. So then we know this Q is from the image. So we are able to find at least one point. So there exists one point such that f of p must be Q. This is guaranteed. So once we get so this guy, then we can now reformulate this phenomena in terms of zero of some function. So let us set new function g with the same domain from F, that this is just nothing but translation. Just take this guy. And we know from the assumption of open mapping theorem, we assume this function is non-constant, by the way. So for the constant case, so this is clearly not possible. So this must be non-constant. So thereby, G should be non-constant as well. So we also know this. So now we know G is non-constant holomorphic function. Then we can, so, and we know G of P is 0. So we have 1, 0. Then from what we already established, we know all zeros are isolated. All zeros are isolated for non-constant holomorphic function so that we can say all zeros of G are isolated. All right, now this is now guaranteed. So thus, we are able to find at least some small neighborhood of P such that containing all limit points of this like the ball. So of course we just exclude this like the center, this like the center. So for any point from here, except like the P, G is not zero, except P. This is we know we can guarantee. So that's why we first like to establish the identity theorem to just make the isolation of each of the like the zeros. Now we have the existence such like a small r. Then we can also look at the boundary of this like the small ball. Then we know this is compact. This is compact. And since G is continuous, so with putting the absolute value with G, this is continuous real value function. So we know we are able to find the minimum. And so in this like the G, so this like the G is never zero, so that we are able to find some positive epsilon such that so the absolute value of G is at least greater than this epsilon for any G on this boundary. And what we'd like to claim is this epsilon is actually the answer of what we want to claim. So this is actually the answer. So we want to show, now we already found what we need. So the small neighborhood of Q with the radius of like the epsilon is indeed the subset inside of this image. If once we establish this claim, then the proof is over. Then what we have is the argument principle. Why the argument like the principle? So we know, so if G has the zero of some order, right? So it has some finite like the order as G has the like a zero there, then we know this n is coming from the remark. This can be written as a boundary integral like this. We know this is guaranteed. And by the way, this expression is also the same as, so if we just rewrite this same expression in terms of the target function f, then g prime is same as f prime, and g is same as f of g minus q. We know these are all equal as just the order of the zero at point P. So this is now guaranteed. So by using this like the fact, then now let us define the following function. So define function h that is from this like the small like the ball. But the interesting point is that so from the argument like the principle, we can say the codomain is not the real or the complex, but it is integer. So that for each of the point of omega, so this is a point within the ball, then we are able to still use this integral like the form so that we are able to find 1 over 2 pi I of this same expression. And still all expressions are exactly the same, except replacing this guy. So this makes sense. So why this is well defined? So, well, let's just think about this one by one. So if you think about the picture, so there's a target point like the Q, and there's a small like the ball, and there's a like the ball already here, the epsilon sub Q, and we choose the arbitrary point from here. from here. So we just need to worry whether or not the denominator might be zero. If just we take the z from the like the boundary of this like the ball of a radius like the r, then we know. So for any like the point, indeed. So for any point from this like the boundary, we know if we just look at this guy, I'd like to claim this never zero, this never zero. And we put the absolute value, we just need to claim that this is always positive. Then by using the triangle inequality, and all we need to compare is with the center, so that by using the triangle inequality, we can say this is greater than equal to the following two quantities. Once we replace omega by q and just take this guy, then by using the triangle inequality, you can see that this triangle, like the inequality definitely holds. Then once we have this guy, then we know f of z minus q, this is less than epsilon. This is the way to construct, because this is way to construct this epsilon. The first part is strictly greater than epsilon, and we can just keep the second part. Then we also know, if you just look at this picture, the distance between omega and q, this is less than epsilon. So this is greater than zero. So that this like the h is well defined. And moreover, so by using the argument principle, we know that this is integer value. This is now integer value. Then what do we know? H is, by the way, from the construction, this is continuous function. Notice that H is continuous and integer value. So this guarantees that such a like the function must be constant. So we can say that h evaluate omega, any omega is same as h evaluate q, which is same as the order at point q. So this is guaranteed. That means if we just go back to the expression of f, so f of omega, f of like the z minus omega. So we know if we establish this like the zero, or in other words, f of z equal omega. So we know there are n numbers of like the zeros. Of course, so including multiple roots, satisfying f of z minus omega to be like the zero. So that means, so we can say that omega belongs to this guy. Because if you choose any point, then we are able to find this omega as a like the image from this like the function. So this completes the proof. All right, so probably this is a good time to finish this like the lecture. It becomes a little bit lengthy. So what I want to say is that, so we argue the identity theorem, we also argue the identity principle, we argue the open mapping theorem, and I also argue the Riemann-Roch like the singularity theorem. So we need to now discuss the like the importance of the pole and the meromorphic functions next time. So this is the video for this week for the graduate class of like the complex analysis graduate class at Texas University, like the week of the last week of the March. So thank you very much for watching this video. Bye bye.